All right, ladies and gentlemen, welcome back to another video with Mr. Kenton and HL Chemistry. And we're continuing our discussion and learning through the D block elements, the first row of the D block elements. And we ended last class by talking about homogeneous and heterogeneous catalysts. But we're going to pick this up and talk about, at least the focus for today, is going to be talking about the multiple oxidation states for our various elements that are in that first row of the D block. Now, one thing that we need to consider as we're getting started is that we've mentioned it already, but zinc is not considered a transition element because it doesn't form multiple ions with incomplete d orbitals, right? If you remember in everything we talked about, zinc always forms a 2+ ion because it loses its 4s electrons, and then none of the d orbitals, none of the d electrons get used, right? So that's an important thing for us to kind of remember going forward, that transition elements are transition elements because their d orbitals get involved in the loss or gaining of electrons, specifically loss of electrons in chemical bonds, right, to form different ions. So kind of keep that in the back of your mind. Now, your transition elements, we know this already, tend to form one or more ions with a partially filled d sublevel, right? We've seen this over and over and over again. Whether it's an honors chemistry or an AP chemistry, still holds true here now, right? Now, like we mentioned, zinc is the only one that forms one ion and does not have a partially filled d sublevel. Zinc has a completely filled d sublevel once it forms an ion, right? And so we're looking at zinc makes the 2+ ion, which has the electron configuration of bracket argon 3d10. Now, not surprisingly enough, should make sense, zinc doesn't make any colored compounds. So when you look at zinc compounds, I guess in the sense of the other transition elements, they're kind of boring, right? There's nothing really unique about them, no crazy colors, no greens or oranges or reds or blues that are being formed within those particular compounds of zinc. Now, when we think about our transition elements, so things other than zinc, right, they're going to show an oxidation state of +2 when the s electrons are removed. So when we think about it, almost all of our first row D block elements are going to have at least one oxidation state that's +2. And that's going to be due to the fact that the s electrons have been removed from their valence shell, right? So when the first row D block elements form ions, they always lose their 4s electrons first to make the 2+ ion. Now, obviously, there's an obvious exception there when we talk about something like chromium or copper, because they have a slightly different electron configuration. Both of those elements would form a +1 ion first. Now, to make ions of higher than 2+ for the majority of those first row D block elements, then you start removing electrons from that 3d sublevel within those particular elements. Now, as we're looking at that, what we should be able to do is explain the ability of the transition metals to form variable oxidation states from successive ionization energies, right? And so one of the things we're going to be looking at is kind of looking at a table and looking at what are the different oxidation states, what are the different ions that these first row D block elements can form. So let's go ahead and take a look at those things, right? So we know that they have variable oxidation numbers, and we know that the S block elements only show one oxidation state corresponding to its group number, right? So like lithium and calcium, for example, lithium's always +1 and calcium's always +2. That doesn't change. Transition elements, however, are going to show more than one oxidation state. And this is going to be related specifically to ionization energy, right? So remember, ionization energy is simply the energy required to remove an electron from the gaseous form of an atom or from an ion, depending on if you're removing an additional electron, and be the gaseous ion removing an electron from it. Right, and so the only thing I would add to that definition, I mean, we kind of alluded to it, ionization energy doesn't necessarily have to be from an outermost electron. You can look at it from removing a core electron, right? It just depends on how many electrons you've already removed in that particular process. All right, so because of the 3d and 4s orbitals being so close in energy, when you start looking at the first row of the d block elements, the electrons can be removed from that 3d sublevel without a huge jump in energy, unlike what you would see from going from, let's say, a p orbital to an s orbital, or s to a p orbital, however you want to look at that, right? So there's a pretty significant jump in energies between s and p orbitals, but that's not the case when you're comparing orbital energies of s and d orbitals, respectively. So we got two examples here. We got calcium, which is one of our group 2 elements, S block, and you got titanium, right? And so we know calcium's more likely to form +2 ion, or 2 plus ion, because it removes that 4s electron. Calcium loses those 2 4s electrons, but if we wanted to try to remove another electron from that 3p orbital, the problem we would run into is that we're removing it from a core electron, and so it's going to be significantly harder to remove that electron from the 3p orbital, right? So we get an increase in Coulombic attraction between the nucleus of calcium and that 3p electron, so it requires more energy. That makes sense. Well, in titanium, losing those 4s electrons, you form the titanium 2 plus ion. Well, because the 3d orbital is relatively close in energy to the 4s orbital, you could remove one of the 3d electrons to make the titanium 3 plus ion, or even another to make the titanium 4 plus ion. All right, now we would stop there, because with titanium, once we remove that 4th electron, if we wanted to remove a 5 plus ion, we'd be removing it from that 3p sublevel, and so we'd be moving again from that jump from 4s, or in this case 3d to 3p. There's a big jump in energies there, and so the +5 ion of titanium is not very common, right? Not saying it's not possible to have, but it's not something that's going to be formed naturally, right? I hope that makes sense to you guys. Now, when you look at this chart, you look at this table, this is showing you the oxidation states of the various first row D block elements. And just to kind of take note, the ones that show up that are in red, those are the most common oxidation states for those particular substances, right? Doesn't mean that the other ones don't exist, that they can't be formed, but the ones in red are the most important ones. So you can see like scandium can form +3. Titanium, as we've seen, +2, +3, and +4. Vanadium goes from +2 to +5. Chromium +2 to +6. Manganese from +2 to +7. And then iron +2 to +6. Cobalt +2 to +5. Nickel +2 to +4. Copper, you got 1 through 3. And zinc +2. And kind of an interesting pattern, which we're going to talk about here. Notice how, as we move across, we just keep adding an additional oxidation state up until we get to +7. And then once we get to manganese, it kind of reverts back. It's like kind of making a V shape there, right? It's increasing and then it goes back down. So note that all transition elements show the +2 and +3 oxidation states. Now, it does make a note here that for any of the transition metals from scandium to chromium, the 3 plus ion is much more stable in those elements, so from scandium to chromium. But on the flip side of that, the metal 2 plus ion is going to be more stable from manganese to copper as you're moving across the period. So there's kind of a little bit of a shift there. Now, the reason for that, this is due to the increased nuclear charge of the later elements, making it more difficult to remove a third electron. Now, the maximum oxidation states increases in steps of +1 until manganese. Now, again, this is due to the use of the 4s and 3d electrons. And then after manganese, the number of states decreases by steps of -1, right? So that's how we saw that it went up at manganese, it went up to a +7 oxidation state. But then as we went past manganese, it went down. It went +6, +5, +4, so on and so forth. So it's kind of a good kind of pattern to recognize when we're looking at the transition elements. Now, when we start looking at oxidation states where you're seeing your metals form a +3 oxidation state or higher, what we start to see is that the bonding there that's taking place within that element, it tends to be more covalent in character than ionic. So rather than it being a transfer of electrons, we start to see that the transition elements can start to display bonds that are more covalent, where there's a sharing of electrons rather than a transfer. And again, this is for oxidation states that are above +3. Now, our compounds that have these higher oxidation states, they tend to be oxidizing agents. And when we get into oxidation reduction chemistry, redox reactions, we'll talk about that term, but you could think about an oxidizing agent as something that is being reduced, right? So it's something that is gaining electrons. All right, so that's going to conclude what I wanted us to look like as it pertains to oxidation states. Thank you guys for joining me. If you guys have any questions, please don't hesitate to ask. Bring your questions to class. I'll be more than happy to address them. I appreciate you guys watching this. Hope it was helpful, and I look forward to seeing you guys again soon. Take care.